The upcoming lab is dimerization of an alkene. You can call it synthesis of isooctane starting with T-butanol. The reaction, in a sense, is very similar to what you did last semester, where you learned about the elimination reaction of what happens when you treat a tertiary alcohol with an acid you heated up. So then what we had done was we took T-butanol, and you can have an ethyl group, I think that's what we had then, and you treat it with an acid, a proton source. So hopefully you can see that this is going to cause protonation, loss of the bisulfate, so you end up with a protonated alcohol and the corresponding conjugate base leaves. Now this is a tertiary center, and so of course you can show the loss of water, which is going to give you a carbocation. What happens next? In this particular case, what we are going to run as a reaction, you're going to run the reaction in an acid reflux. What that means is that you will have a round bottom flask. You're going to connect it to the reflux condenser, water in, water out. So you're going to allow the vapors to come back, fall back in, again rise up, fall back in. So it's going to continue to take place for a long period of time. What you did last semester, however, was that as the reaction takes place, you connected this to a still head, which was connected to a receiver flask, and then you collected your product. So essentially your product, which is isobutene, would rise up. Since it's a gas or a low melting liquid, it would get to the receiver flask and you separate it out. So that is the basic difference, that what you did last semester was a beta elimination reaction when HSO4 negative would pick up this proton and give you isobutene, which was what was collected as your product. On the other hand, now this isobutene is going to be thrown back into that acid broth, so it's going to see another reaction, and that's what we are interested in learning about. So what you're going to see as a second part of the reaction is that once that isobutene is formed, it has a really low boiling point of like 33 or 34 degrees Celsius. So when that sees more of the proton, what happens? It is going to form the carbocation, and it's going to be tertiary versus the primary, and of course tertiary is going to win. So that's going to be your more predominant or more stable carbocation, and you have another alkane which is going to attack at that particular carbon. So one molecule is going to act as the nucleophile, the other is going to act as the electrophile. And when that happens, let's perhaps number this. So 1, 2, 3, 4, 5, and 6. You're going to end up with carbocation is at 2. Position number 4 is what is interacting. So you have a choice. You could have a carbocation right over here, or you could have a carbocation versus a carbocation if 5 attaches, and that would mean you have 1, 2, and 3 carbons, which will give you a primary carbocation. Hopefully everybody can see that the first carbocation is the more predominant one. The second one doesn't even get formed because primary is way too energetically unstable. And now you have a choice to lose a proton. So either you can lose one of these 3 hydrogen atoms, or you can lose one of the two sandwiched in between at position 4. And hopefully one can see that if you lose these protons, they are way too sterically hindered by the T-butyl group, by the isopropyl group here. So even though that particular alkene is more stable because it's more substituted, it's going to be your minor product. So this guy is your minor product, and the other one that is basically formed by the loss of one of the three hydrogens as the proton, that is going to be your major product. And the main reason for that is steric hindrance. Now, when you read through the reaction procedure, you have to begin with 10 milliliters of water and 10 milliliters of concentrated sulfuric acid. As you do the addition, please do so in the hood, and you always want to add acid to water, not the other way around. So water, 10 milliliters would already be present. You're going to add 10 milliliters of H2SO4. You always want to add acid because water has a really high specific heat, and so it's a safety measure, it's a safety feature. If I were you, like I said, I would do that in the hood. So do it in the hood. And also try to cool it down in ice. The reason why you want to do that is because this reaction is exothermic in nature due to the formation of the hydronium ion. So that means that, the second step where it says cool the solution to 50 degrees in an ice water bath. Since you already have it in ice, that temperature would actually never even reach 50 degrees. So even if you're at 20, 30, that's okay. So you can probably ignore step number 2. At this point of time, you would then add slowly with continuous swirling. You're going to add the alcohol, the T-butanol, and you would do that as a slow addition. It's possible that as you're adding, you might hear a crackling sound, or you might hear the development of some color. Try to maintain a pace, like, a slow addition, a dropwise addition, because if you add too much of the alcohol too quickly, charring of that alcohol can take place because of the presence of H2SO4, and that will cause in loss of yield. So let's make sure that you fully mix the solution, and you make sure that you do this slowly. Nice and slow is a good way to go about it. After you have added your alcohol completely, and it's nicely mixed, you can set it for a gentle reflux and boil it for 30 minutes. We are going to do that in the hood. So that's a reflux condenser. So what that means is you will have your round bottom flask that will be connected to a condenser, water in, water out, tube within a tube system. Water in, water out. Here's your reaction mixture. We will have the heating mantle. Obviously, you're going to clamp this. You're going to also clamp the reflux condenser, and you're going to heat it in the heating mantle for a gentle reflux. And you heat it for about 30 minutes. So while this is being heated, we'll do the additional assignment. Now, as you have completed your 30-minute period, during that time, essentially you will cool the reaction. You will allow the reaction mixture to cool down, and then you will transfer it into a separatory funnel. So that's your separatory funnel. So you pour down your reaction into that separatory funnel, and you're expected to see 2 layers, one for the non-polar product, and second for the polar reactant, which is aqueous acid, essentially. Since it's greater in density, that's going to be the lower layer. Just in general, unless you have hydrocarbon which contains heavy atoms like chlorine or bromine, consider hydrocarbon type compounds to be to weigh lesser, and so the density is going to be lesser, and that should be your topmost layer. So you're going to drain off the acid part completely, collect the top part, and just add an equal volume of water into this layer. The whole purpose is to remove any traces of any acid that might be present. And once you have done that and collected the layer again, you're going to place it, you're going to transfer that into an Erlenmeyer flask. And to that you're going to add approximately 1 gram of calcium chloride. You can, if you want to, use sodium sulfate. Those are other choices. You can even use magnesium sulfate for that matter. The whole idea is to use it as a desiccant and basically get rid of any moisture. At this point of time, I would say 60% of the class gets a relatively pure material, and they don't need to carry out the second distillation. On the other hand, a lot of times we see that the distillation hasn't, or the drying process rather, hasn't quite worked, and so in that event you would have to add 2 boiling chips and carry out a simple distillation to collect the fraction that boils between 100 to 110 or so. But like I said, most people are usually done with that. So if I were you, I would, once you have dried it up for approximately 10 minutes or so, I would take a quick IR, I would take a GC, kind of get an idea of if there's any moisture before you decide whether you need to carry out a distillation or not. And then just basically calculate the percent yield. So in this particular lab, you're going to carry out a GC, you're going to carry out an IR, of course there's going to be percentage yield, and you're going to run a chemical test. The chemical test is similar to what you learned, or what you ran actually in Organic 1 as well, that you treat it with KMNO4. So you're going to take 3 to 4 drops of your product. You're going to dissolve that in 1 milliliter acetone, and you're going to add to that 5 to 7 drops of KMNO4. If you have a double bond, essentially the pink color of KMNO4 gets discharged, and it either becomes colorless or develops like a slight yellow color due to the formation of MnO2. And that's what you're going to record. Your starting material is a tertiary alcohol, and tertiary alcohols do not undergo oxidation. We'll learn about that in chapter 17. So this is a great technique to run the reaction for the case of the product as well as your reactant, and see for the identical conditions which one has a persisting pink color of the KMNO4 and which one goes colorless, and then discuss that in your conclusion section. The way you report your chemical test is you make a little table. You say experiment, you make an observation, and then you have inference. So you say A, 3 to 4 drops of the product dissolved in 1 milliliter acetone, 5 to 7 drops of 1 millimolar KMNO4 was added. And then you make your observation, and then what you infer from there. And then you do the same thing for the starting material. You write a similar statement. You make the observation, you infer that, and then you discuss that in the conclusion section. So you have to discuss all 4, the percent yield, the chemical test, the IR, as well as GC. And what you discuss, how successful your reaction was, uh, really is a combination of everything. Let's say you ran your reaction in the chemical test. You clearly see that the product is indicative of the double bond. In the IR, though, you see the double bond, but in addition to that, you see an OH as well. That OH could be water, because maybe your desiccant didn't work very well, or you didn't add enough desiccant, or maybe you didn't give it enough time. So those are, couple sources of error that you should think of, and discuss that. On the other hand, everything might just tally perfectly well and come together for you. That's a possibility. So whatever it is, discuss that in your conclusion section. Make sure that you attach your GCs and IRs, labeled GC and IR, and turn it in the next week. That is it.